Hello. Over the course of this video, I will demonstrate using Wolfram Mathematica 9 how to find the shortest distance between two straight line segments. I'll begin with a statement of the problem. Find the shortest distance, d sub min, between two straight line segments PQ and RS, where the points PQ, R, and S are defined as in the problem. I'll begin by fixing parameterizations of the line segments. So I'll define a function for PQ from the point P, 6, 0, 0, with the direction and magnitude of the vector PQ, which would be -11, 0, 0, times the parameter t, and a function for RS from the point R, 0, 0, 11, plus the direction and magnitude of the vector RS, 0, 0, 6, times the parameter S. And I will identify the domain of these functions Now, I will minimize. No, first I need to actually define a function of the distance between the two line segments. So, I will define a function d. So d is, applying the distance formula, the square root of 6 minus 11t minus 0 squared plus, and as a formality, I'm going to add 0 minus 0 squared plus 0 minus 11 plus 6s squared. Now, I want to minimize the distance function over the domain rectangle defined here. So, I have the partial of d with respect to t, and I have the partial of d with respect to s, d with respect to s. Now I want to solve for d sub t and d sub. I want to solve for the gradient vector equaling 0 for t and s. Alright. No solution exists. Oops. Let's make that plain text. No solution exists within the domain rectangle. So what I need to do is minimize the function over the boundary of the domain rectangle. So, I'm going to define some vertices of the domain rectangle using the vertices A, 0, 0, B, 1, 0, C, 1, 1, and D, 0, 1 of the domain rectangle. I'm going to fix parameterizations of the segments comprising the boundary of the domain rectangle. So I have AB, let's make it a function AB, equal to the point A, 0, 0, plus the vector AB, 1, 0, times the parameter t. And I have a function of BC equal to the point B, 1, 0, plus the vector BC, which is 0, 1, times the parameter S. And I have a function CD equal to the point C, 1, 1, plus the vector CD, which is negative 1, 0, times the parameter t. And I have a function of dA equal to the point D plus the vector dA, which is 0, 1, 0, negative 1, times the parameter S. Alright. So now what I need to do is minimize the function over each of these segments. So I want to take the function d, evaluated at t is t, and s 0, as in my function f sub ab. And I want to minimize this function. So I'm going to call this d of ab. And I want to minimize this. So I want to find the derivative d sub ab with respect to t. And I want to solve for that equals 0. So let's try solve for this equal to 0 for t. Alright. Now, I also want to evaluate d along BC. So I have d evaluated along when t is 1 and s is s. And I want to minimize this function. So I want to solve for when the derivative of d bc with respect to s is 0 for s. Alright? Now, d sub cd equals d evaluated at t is 0 and s, oops, wrong one. T is 1 minus t, 1 minus t, and s is 1. And I want to find the minimum of this. So alright, and finally I have d sub dA equals d evaluated at t is 0 and t is 0 and s is 1 minus s. Now I want to minimize this. Solve for the derivative of d sub dA with respect to s is 0 for s. Now, evaluate the distance function at each critical point. And identify the minimum value. So first I have d, my distance function, evaluated at t is, let's start with t is 6 over 11. So 6 over 11, and when t was 6 over 11, remember that s was 0. Now I have d evaluated at t is 1 and s is negative 11 over 6. Now I have d evaluated when t is 5 over 11 and s is 1. Finally, I have d evaluated at t is 0 and s is 17 over 6. Now, alright, next I evaluate the function at the vertices of the domain rectangle. So I have t is 0 and t is s is 0 and d evaluated at t is 0, say t is 1 and s is 0. D evaluated at t is 1 and s is 1. And finally, d evaluated at t is 0 and s is 1. Now, eliminating extraneous solutions. Which would be this and this, because this s does not lie within the domain of my domain rectangle. Neither does this, because this is greater than 1, this is less than 1. So, I wonder if I can strike through this anyway. Ah, well, I'll just ignore it. I'm going to sort the remaining solutions. So, I have 11, and I have square root of 290, and I have square root of 157, and square root of 146, and square root of 314, and finally the square root of 5 times the square root of 13. Alright, this indicates that the answer is 11.